The aim is to draw the state diagram for a transition detector. That means we have a stream of 1-bit numbers coming in, and the output is going to be normally a 0, but it will be a 1 whenever the input has transitioned from 0 to 1 or from 1 to 0. And we want our finite state machine to be a more finite state machine, so the output just depends on the current state. As usual, we start with our starting state. In the starting state, the output should be a 0 because we have not yet detected a transition, and we need to label this as our starting state. I've yet to give this state a name because once we've progressed a bit, we will work out how our finite state machine is going to work, and therefore we will figure out an appropriate label for this node. The input is a 1-bit input, so we have to have two transitions here, one if the input is a 0 and one if the input is a 1. Now, because we're trying to detect a transition, we need to remember what this input is for next time, because if, for example, the input is now 0 and next time it's a 1, well, that's a transition. And to detect that, I need to have remembered that the input prior to the 1 was a 0. So I need new states here and here. And in this state, this is remembering that I received a 0. So I'll just call it a 0. And this one's remembering that I received a 1. So I will call it a 1. Now in both cases, since we've just started and this is the first symbol we've received, then we haven't yet detected a transition. So I've got a 0 here and here. Looking at the first node, well, we've completed it because it's got outgoing transitions for all possible inputs. I haven't labelled the starting state yet. I'll just call it start. And we move on to the next node. So we do the same thing here. I either have a 0 at the input or I have a 1 at the input, and I need to figure out what to do. Well, if I have a 0 at the input, then I have not detected a transition because my previous input was a 0 and my current input is a 0, so no transition. And basically I just want to wait until I get a 1. So in other words, if I get a 0 here, I do nothing. I just return to this waiting state. On the other hand, if I get a 1, well, that means I've detected a transition. So I can label this state 0, 1, and I've detected a transition, so I've got a 1 here. And we'll come back to this presently. Moving over to the node on the right, same sort of argument. I've detected a 1. If I get another 1, then I do nothing because it's not a transition. Not a transition from 1 to 0. So I just go back and wait. If on the other hand I get a 0, well, I've detected a transition. I've detected a from 1 to 0, and I will output a 1 to signify that I've found this transition here. Okay, so the first 3 nodes are done. Now we look at the bottom 2. If we go over to this node again, what do I do if I get a 0? What do I do if I get a 1? If I get a 0, that means that I will have received a 1 followed by a 0. So that means that I've detected another transition, and from my state labeling, it means I should go over here to signify that I've received a 1 followed by a 0. On the other hand, if I receive a 1, that means that my last 2 inputs were a 1. You see the 0, 1 here for the state tells me that I saw a 0, then a 1, and now I've seen another 1. So the previous input was a 1, and the current input's a 1. So 1, 1, that's not a transition. So what I really want to do is I want to wait for a 0. And I could create a new state called 1, 1 to demonstrate that, but that's redundant because if we think about it, all we really care about is that we have observed the previous inputs are 1 and now we're waiting for a 0. So go over there. By symmetry, if we're in this state and we get a 0, that means that we want to go over here because the previous symbol was a 0, and the current input's a 0. So we're basically going over to this state here because we're waiting for a 1. As soon as we get a 1, we've detected a transition. On the other hand, in this state here, if I get a 1, well, my previous input was a 0. My current input, if I now get a 1, that means I go over here. I've detected a 0 followed by a 1. So I've got a 1 down here. And for our first attempt, this is the state diagram. However, it's a little bit messier because we insisted on not detecting any transitions right at the very start. So here we have an example of a start state that we never revisit. Now, often when you first start something up, it doesn't really matter whether you might have a false detection or not. So let's assume when we started it, we just immediately started in this state over here. Then that's not such a bad thing. It does mean if the very first input is a 1, I will have detected a transition, but maybe we can live with that, and that would then simplify our state machine. You see, currently we've got 1, 2, 3, 4, 5 states, and that means that I need 3 flip-flops to store 5 different states. Whereas if I got rid of this starting node here and just chose to start either here or here, then I'd only have 4 states and I'd only need 2 flip-flops. The other realization we can make is that here we've labelled these nodes 0, 1 and 1, 0 to correspond to I first received a 1 and then a 0, and that put me in this state here. Over here we just have a single digit. But how can we arrive in this state? Well, we can arrive in this state via a 0 here. We can arrive in this state via a 0 here. Or we can arrive in this state via a 0 here. And so again, if we ignore this very starting one, whenever we're in this state, it's because the last 2 inputs were both a 0. So in fact, we can call this state 0, 0. And by a similar argument, we can call this state 1, 1. And we see that what we're actually doing is we're simply just remembering the last 2 inputs. So with this in mind, we can start again and quickly draw an essentially analogous state diagram, but we're going to leave off the starting state. We now know that we want to have 4 states, and each state will represent the last 2 things that we observed in the input. So in no particular order, I've got this. So if I'm at this node here, it means the last 2 inputs were both 0. So that means there's no transition. And if I get another 0, well, that means that my last 2 inputs are still 0, 0. I go back here. Whereas if I get a 1, that means that my last 2 inputs are now a 0, 1. So I will transition over here if I get a 1. This state's done, so move on to the next one. If I'm in the state 0, 1, that means that there's been a transition. The input changed from a 0 to a 1, so I denote that with a 1 here. And I ask, if I get a 0 coming in next, well then the last 2 things I've seen would be a 1 followed by a 0. So I therefore transition down here if I were to get a 0. If I were to get a 1, then the last 2 things I would have seen are a 1 and a 1. So I transition down here if I get a 1. And now I've done the top 2 states. Bottom left state, if I have a 1, 0, that means that a transition's occurred, so I denote that on my output. If I receive a 0, then the last two inputs would have been a 0 followed by the 0 I now get, so I move to this state with a 0. Whereas if I get a 1, then that means the last two inputs would be a 0 followed by a 1, so I go back up here if I get a 1. This brings us to the final state, 1, 1, so the output's a 0. If I get a 1, then I just transition back here. If I get a 0, then the last two inputs are a 1, 0, and hence I go over here if the input is a 0. Now, if we haven't made any mistakes, this diagram and this diagram should be the same. So 0, 0, 0, with a loop back if there's a 0, and a transition to 0, 1 on a 1. So yes, this one's correct. 0, 1, we're outputting a 1. What are the transitions? We only have to look at the outward transitions. If all the outward transitions are the same, then the whole diagram must be the same. So the outward transitions, if I get a 1, I go down here to 1, 1. If I'm here and I get a 1, I go down here to 1, 1. If I'm here and get a 0, I transition to 0, 1. If I'm here and get a 0, I transition to 1, 0. Sorry, I called this one 0, 1 just before by mistake. It's 1, 0. And it should be 1, 0, so that's correct. Nevertheless, proceeding in this way, we can check that this state diagram is the same as this state diagram, just with the start removed. The Verilog implementation of this is actually very easy, as you'll see in the lecture notes, because I can basically use a shift register to store the last two inputs. And then the output is simply the exclusive OR of these two bits, because an exclusive OR will tell me if one of them's a 1 and one of them's a 0, i.e. if a transition has occurred. So that's it. This is the typical state diagram you will see for an edge detector using a Moore finite state machine.